Hey guys, welcome back to my channel camnotion.com. So as you can see, we are going to discuss the last questions of this question paper, and this is presented by me Amarjit. And if you guys if yet not subscribed to my channel, do subscribe and give a thumbs up. Right, so let's get started. The first question: the change in entropy accompanying the heating of 1 mole of an ideal gas from 300 Kelvin to 600 Kelvin at constant pressure. So we need to calculate change in entropy, which can be given as del S is equals to del S represents the change in entropy, which can be given as n Cp ln T2 by T1. Right. This is the expression for change in entropy in terms of temperature when pressure is constant. Right. So here the gas is present as 1 mole gas is heating, so heated. So n values will be 1, n value will be 1, and that is Cp ln, and the final temperature which mentioned here is 600, and T1 is 300 Kelvin. So if you solve it, it would be Cp ln 2. That's right. So del S will be del S would be Cp ln 2. For this question, option A is the right option. The change in entropy is Cp ln 2. Right. So for this question, option A is the right option. And moving to next question. Right. The integrated expression for the rate constant of second order reaction when both the reactants are same. So in case of second order reactions, we always have two conditions that when the reactants may be same or the reactants may be different. So when the reactants are same, which talking about in this question, if we talking about in this question that here the reactants are same as mentioned, so it's for rate constant can be given as 1 by T x by m a into m minus x, where x is the concentration of product at any time T, and A is the initial concentration of the reactant, and A minus X represents the concentration of the reactant when at any time T, right? So for this question, option B is the right option. Also, this is the expression when both the reactants are different. That is, A is the concentration for one product, and B is the one reactant, and B is the concentration for the other reactants, right? So when the reactants are different, so this is the rate expressions for second order reactions. So for this question, option B is the right option. So moving to next question. The standard reduction potential E0 for half cells reactions, which is given as for Zn2 plus to Zn Zn, the reduction potential is given as E0 is equals to minus 0.76 volt, and for Fe for this half cell reaction, that is Fe3 plus is converting to Fe2 plus. Here the reduction potential is given as E0 is equals to plus 0.77. Now we need to calculate the EMF of the cell. Now we know that EMF of the cell can be given as E cathode, right? E cathode minus E anode, right? E cathode minus E anode. So this is the expression through which we can calculate the EMF of the cell. Now E cathode is given here. Now E cathode, the larger value, we always consider the larger value as E cathode, and larger value in terms of reduction potential with larger value is E cathode, and reduction potential with lesser value, that is for first half cell reaction, that is zinc 2 plus when converted to zinc solid, that is E0 is equals to minus 0.76, and this value will be E anode, right? So if we put those value in here, minus 0.76, so if we solve this, we will get 1.53 volt, and this is the EMF of the cell, right? So E cathode minus E anode, the larger value is E cathode and the lesser value is always E anode. We always consider this, and the EMF of this cell is 1.53 volt. So for this question, option B is the right option. In this question, if K is less than 1, then del Z naught will be, right? This is a question from chemical equilibria, and we know that the del Z naught can be given as del Z naught equals to minus RT ln K, right? This is the expression for del Z naught. So when the k value is less than 1, when k value is less than 1, the del Z naught always positive, right? Del Z naught is always positive, and when k is equals to 0, and when k is equals to 0, del Z also 0. These are to consider. These are two conditions, that when k is less than 1, del Z is always positive, and when k is 0, that is equilibrium constant is 0, then del Z naught is also is equals to 0. So for this question, when k is less than 1, it would be positive. Option C is the right options, right? In this question, the strength of laboratory HCl solution is 12 N and 12 normality, and the amount in ml of the HCl solution required to prepare 600 ml of 1 normality HCl, 600 ml of 1 normality solutions. Now, the relation here is N1 V1 is equals to N2 V2, N2 V2. N1 is here 12, and V1, which we need to calculate, and N2 is 1 normality, and V2 is 600, right? So if we solve it, then V1 will be 50 ml, that is 50 ml of 12 normality solutions is required to prepare 600 ml of 1 normality solutions, right? For this question, option B, 50 ml is the right options. If the pKa of any 4 acids A, B, C, D are 1, 2, 3, 4 respectively, the stronger acids are. Now, pKa is equals to minus log Ka. pKa is always minus log K. So the acids with lesser pKa value, acid with lesser pKa value will be the strongest acid, and acid with higher pKa value is the it is least acidic, right? So here acid A has pKa value is equals to 1, which is the least among the 4. So A will be the strongest acid among A, B, C, D, and D will be the weakest acid, right? So for this question, that is the strongest acid among A, B, C, D will be A, right? So moving to next question. A particle inside a 1D box of length L has a potential V, and outside the box potential is infinity, and the energy state is n is equals to 0, which is not allowed, right? So for this question, that is the question is basically asking about when that n is equals to, when n is equals to 0, that E naught, that is when n is equals to 0, the energy state is not allowed, that is E is equals to 0, which is not allowed actually. That is this is because of the fact that when n will be 0, the psi also will be 0 in everywhere, right? And which is actually not possible, because we are taking the particle in the inside the 1D box, right? And if the psi would be 0, then it would signifies that its wave function will be 0, and which is not possible, because we are actually taking the particle inside the 1D box, right? And its wave function is always signifies the particle existence, right? So the psi must have any integral value, right? So when psi is equals to 0, it can't be possible. So for n is equals to 0, the reason why it is not allowed is that its psi value will be 0 in everywhere. So for this question, option C is the right option. This is a question from point group group theory. The point group of BrF5, bromine pentafluoride, and you should know the structure of bromine pentafluoride, which is a square pyramidal structure, and fluorine Now as you can see, there is a C4 axis, C4 axis is present here, and there is no perpendicular C2 is present. So and 4 sigma V is there, so its point group will be C4V, right? For this we can calculate that its point group is C4V. So moving to next question, 9 gigahertz when converted to per centimeter, which is equals to, right? The relation between centimeter, that is wavelength in centimeter, which is equals to, which defined as 29.979 by gigahertz, right? This is the relation which relates the centimeter in terms of gigahertz, right? So 29 by 979 by 9, and if you reverse it you will get centimeter inverse, right? For centimeter inverse it will be 0.303. So the centimeter inverse it will be 0.3, right? So 9 gigahertz is equals to 0.3 per centimeter. So for this question, option B is the right option. And a particular molecule undergoes a spectroscopic transitions between ground state and an excited state with lifetime 0.1. The approximate uncertainty in the energies in its excited state energy level, right? Now according to uncertainty principle, the uncertainty in energy and time which can be which is equals to h by 4 pi, right? This is the expression which is equals to 4 h by 4 pi, and if you put 0.1 here, and that which is the uncertainty time, the energy will be 5.27 into 10 to the power minus 34 joule. That is this is which is there in option A, that is 10 to the power minus 34 joules. So and the uncertainty in the excited state energy level is 10 to the power minus 34 joules, and this is the expression from uncertainty, Heisenberg uncertainty principles, right? So these are the last questions of this question paper, and if you like this, give a thumbs up, right, and share it. Thank you.